We're now going to investigate the connection between the invertibility of a matrix and row-reduced echelon form. Before we can state our main theorem, we need a couple of lemmas. Here's the first one. It says that if X is an n by n, so a square matrix in row-reduced echelon form, then either it is the identity or it has a column with no leading entry. The method of proof is to suppose that the latter case doesn't hold and then show that actually in this case X must be the identity. So we'll assume throughout that X is in row-reduced echelon form and that every column has a leading entry and prove that X must be the identity. So if every column does have a leading entry, then every row has a leading entry as well. There's the same number of columns as rows, and there can only be one leading entry per row. So let's now let Ci be the number of the column of the leading entry in row I. So just to get a handle on what's going on here, let's suppose that for a moment X wasn't square, but it looked something like this. 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Well, in that case, C1 is the column in which the leading entry in row 1 appears. That's 1. C2 is the column in which the leading entry in row 2 appears. That's 3. C3 is the column in which the leading entry in row 3 appears, and that is 4. We're just numbering those columns so everybody can see what's going on. That's what's happening. Okay, the row-reduced echelon form condition tells us that C1 must be less than C2, must be less than C3, and so on. But C1 up to Cn are all numbers between 1 and n. So the only way you can have this strictly increasing sequence of numbers between 1 and n is if C1 is 1, and C2 is C2, C2 is 2, up to Cn is n. But columns which have leading entries must have zeros everywhere else, again because of the row-reduced echelon form condition. So the first column of X has its leading entry in row 1 because C1 is equal to 1. That leading entry must be equal to 1 because X is row-reduced echelon form. Every other entry in that column must be 0 because X is row-reduced echelon form. So the first column is 1, 0, 0, 0, 0 down to 0. Let's look at the second column. C2 is equal to 2, so the leading entry appears in row 2. Every other entry in that column must be 0 because X is row-reduced echelon form, and the leading entry itself must be 1. So the second column is 0, 1, 0, and then a bunch of zeros, and so on. But these columns are the columns of the identity matrix. Therefore X is the identity matrix. Moving on, we need another technical lemma, which is that if E is invertible, and if A is a square matrix of the same size as E, then EA is invertible if and only if A is invertible. First of all, let's assume that A is invertible. Well, in that case, E times A is an invertible matrix times an invertible matrix. Products of invertible matrices are invertible, and therefore EA is invertible. Conversely, let's suppose that EA is invertible. If its inverse is B, then EA is the inverse of B, so EA is B to the minus 1. Now, multiplying both sides of this equation on the left by E inverse, we get that A is equal to E inverse B inverse. But the inverse of an invertible matrix is invertible again, so E inverse is invertible and B inverse is invertible. So here is A written as a product of invertible matrices, and therefore A is invertible. Having proved those two technical lemmas, we're now ready to state our main theorem, which is that an n by n matrix A is invertible if and only if there exists a sequence of row operations R1 up to Rk for some natural number k, such that when you do that sequence of row operations to A, you get the identity matrix. So here I'm writing I instead of IN, just to keep things shorter. Again, this is an if and only if theorem, so we should do both directions. Let's start with the if direction. So suppose such a sequence of row operations exists. We will then let EI be the elementary matrix associated to the ith row operation. We know that doing R1 to A is the same as left multiplying by E1. Similarly, doing R2 to R1 of A is the same as left multiplying R1 of A by E2. So doing that sequence of row operations to A is the same as multiplying it on the left by E1, then E2, then E3 up to EK. In other words, because that sequence of row operations takes A to I, it must be that A multiplied on the left by E1, then E2, and so on up to EK equals the identity matrix. We've reached this equation. But we know that elementary matrices are invertible. And we know that a product of invertible matrices is invertible. So the product EK minus 1 down to E1, which I'm going to call E, is also invertible. Now I have that E times A is the invertible matrix I, and therefore A, which is the inverse of E, is invertible too. So we've proved if there is a sequence of row operations taking A to the identity matrix, then A is invertible. Now we have to do the other direction of the proof. So for the other direction, suppose that there is no sequence of row operations which takes the matrix A to the identity matrix. Well, what we know is we can do a sequence of row operations to any matrix and end up with a row-reduced echelon form matrix. So it must be possible to do a sequence of row operations to A and get a row-reduced echelon form matrix. Let's call that row-reduced echelon form matrix X, and that cannot be the identity. Now the first lemma above says that X, being a square row-reduced echelon form matrix which is not equal to the identity, must have a column with no leading entries. So since there's only one leading entry per column, there must be n-1 or fewer leading entries. That means there's a row of X with no leading entry. And a row with no leading entry must be all zeros. So X is a matrix which has an all zero row, and we have seen before that matrices containing a row of all zeros are not invertible. But using precisely the same argument as before, there is an invertible matrix E such that E times A is equal to X. E is the product of the elementary matrices associated to the row operations which took A to X. Since X is not invertible, by the second lemma we proved A is also not invertible. So we've now shown that if there's no sequence of row operations taking A to the identity, then A is not invertible. That completes our proof of the other direction of our theorem. Let's use this to produce another characterization of invertible matrices. Our final theorem says that a square matrix A is invertible if and only if the only solution to the matrix equation A times X is equal to the zero vector is the zero vector. Just to make the notation clear, what I mean by this bold zero here is the matrix all of whose entries are, is the vector all of whose entries are 0. So the vector with the same height as A, all of whose entries are 0. Again, this is an if and only if theorem. So let's begin with the easy direction. If A is invertible, and if V is a solution to the matrix equation A times X equals 0, then multiplying that equation on the left by A inverse gives us that V is equal to A inverse times the 0 vector. But of course, when you multiply the 0 vector on the left by a matrix, you always get the 0 vector again. So the only solution V is actually equal to the 0 vector. Conversely, let's suppose A is not invertible, and we have to prove that there is a solution to that matrix equation other than the 0 vector. Well, if A is not invertible, then we can do a sequence of row operations to A, ending up with a row-reduced echelon form R, which must not be the identity matrix by our previous theorem. Now R must have a column with no leading entry because it is a square row-reduced echelon form matrix which is not the identity. If there's a column with no leading entry, then there is a free parameter in the solutions to the matrix equation Rx equals 0. That's because if you have a system of linear equations whose augmented matrix is in row-reduced echelon form, then the variables corresponding to columns with no leading entry can be chosen freely. They're free parameters. In particular, if you can choose them freely, then there are infinitely many different solutions to the corresponding equations. But the solutions to Rx equals 0 are the same as the solutions to Ax equals 0. That was the whole point of our row-reduced echelon form method for solving equations. So Ax equals 0 also has infinitely many different solutions. There is also a free parameter in the solutions. In particular, there must be a non-zero solution.